A very good, a very good evening to our external panels, all lecturers and fellow students. My name is Kosibo and I'm from Department of Industrial Engineering. Today, I'm going to present about my FYP poster entitled Design and Developments of Latex Card Collector Robots Mechanical Parts. So, without further ado, let me start my presentations. So first, for the abstract, a latex card collector robot is designed and developed in hopes to assist the rubber workers in the latex collection process. This robot is acquired with rear-wheel drive, double wishbone suspension, ultimate steering transmission, and a 4-degree of freedom manipulator to execute their functions. Besides, to test for this robot mechanical stability and dynamic performance, this robot is also undergone with several simulation and experiments. But what leads to the intention of this project? This is because the rubber production around the world has reduced in recent years, especially in Malaysia. And this is mainly caused by the health issue among the rubber workers, the reduction of young manpower in the rubber industry, and also the preferred latex harvesting mode in Malaysia. So the involvement of robot in latex harvesting process can help to improve the current situations. So 3 objectives has been constructed in this project, which is first to design a robot that can move on different terrain surface with a 4-degree of freedom movement robotic arm to collect latex card at different heights. Then is to analyze and evaluate the robot design by using the finite element analysis and motion study analysis by using the SolidWorks software. And lastly is to develop and fabricate a workable prototype for the design robot by using the 3D printer. Then the methodology flowchart is also constructed in this project. The project starts with the problem statement to determine the issue to be improved in the rubber industry. Then the literature review is conducted. After selecting the suitable design concept, the prototype design and firmware selections are carried out. After that, simulation and analysis is carried out to test for the practicality of the design. If the design is practically workable, it is proceed to the prototype fabrication and assembly. After that, prototype test run is conducted to test for the functionality of the design. When the prototype passed the test run, data collection and analysis are done, and lastly come up with the conclusion and recommendations. So now let us move on to the result part. So this figure 2 shows the prototype of the latex card collector robot in this project, and this is the specification of it. And now let us move down here to the result of the simulation and analysis first. So in finite element analysis, robot platform and also the robotic arm are used to test for the effect of the mechanical structure towards the external loads. So in FEA result of robot platform, the maximum stress experience is 2.589 times 10 to the power of 6 Newton per meter square at the center of the robot platform, while for the maximum displacement is located at the 2 center sides of the robot platform with the value of 0.1494 millimeters. Then for the FEA result for a robotic arm, both the maximum stress and maximum displacement are located at the gripper end. This is because gripper end is where the latex card is located and is held. So for the maximum stress, it is 8.676 times 10 to the power of 5 Newton per meter square, while the maximum displacement is 0.1868 millimeters. And these two parts, robot platform and also robotic arms, will not be failed because their maximum stress did not exceed the PLA plastic yield strength, which is this value. And the PLA plastic is the input material to print these two parts. All right, and then let us move to the motion study analysis. The prototype is needed to travel on the track with 2 15 millimeters height barriers to simulate the unstructured terrain in the rubber plantations. And the result obtained from this motion study is in terms of pitch, yaw, and roll angle. Okay, so from this graph, we can observe that for the roll angle, which is represented by this blue line, the maximum degrees that we can obtain is about 3.5 degrees for both sides. And then for pitch angle, it is below 2 degrees for both sides, as well as the yaw angle, it is also below 2 degrees for both sides. As a result, the prototype can travel on the track that with 50 millimeter height barrier. As from the result obtained here, the angles are all small. So now let us move on to figure 3 and figure 4 that shows the video snapshot result of the prototype test run. So figure 3 shows the manipulator test result, and 3 bottles are used to represent the rubber tree, and the 3 latex cups are placed at different height, which are 160, 120, and 105 millimeters height, respectively. So let me briefly explain the working process of the manipulator subsystem. So first, there's a cameras on top of the robotic arm to scan the QR code that stick on the water bottle, and then the camera will transfer the QR codes and sends to the robot microcontroller. And lastly, the robot controller will call out the functions that execute the robotic arm motions to collect the latex cup. As a result, the robotic arms can collect all of them by itself, as you can see from these 3 figures. And then let us move on to figure 4, which is the result of the functional test, where the prototype is needed to perform 1 working cycle. So the prototype is placed perpendicularly and 60 centimeter towards the water bottle. Then the prototype is travel straight until the left ultrasonic sensor sends the water bottle. After that, the prototype will start to reverse, stare, and turns towards the water bottle. When the front ultrasonic sensor sends the water bottle, the prototype will stop, and then the robotic arm will start to perform its task to collect the latex cup and pour the water from the latex cup into the latex storage tank through the funnel. After pouring, the latex cup is placed back to the water bottle, and the robotic arm is moved back to its original positions, and then the prototype will start to reverse and return to its traveling path and proceed to the next process. So, this process takes around 107 seconds to complete 1 working cycle. And this is the working cycle of latex collecting process. So this is a small discussion about the result I have explained just now. And now let us move to the last part, which is conclusions. So in conclusions, all the objective has been achieved. A latex cup collector robot that can move on unstructured terrain and can grab the latex cup with different height is designed and developed. It is analyzed and verified by simulation and test run. And the result shows that this design is feasible to be used as it is mechanically stable. So for the future recommendations, 1 more degree of freedom can be added to the manipulator to reduce the working step and also the working cycle time. So that's all for my presentations. Thank you.
Okay, thank you. Thank you, Khor. Right, any questions from the floor, especially the judges? Okay. If no, all right, thank you, Khor, for your presentation. Yeah.
Yeah, thank
Now
you.
we